So this is one of our primary tools for surface and interface characterization of molecular electronic materials. This is known as a photoelectron spectrometer. We have two primary techniques that we use this for: X-ray photoelectron spectroscopy and UV photoelectron spectroscopy. The sample is positioned inside this high vacuum analysis chamber. Excitation by either X-rays through this monochromatic source here or UV photons back here creates a photoelectron emission from the surface that's collected via these electrostatic lenses inside here, and finally a hemispherical analyzer here with multi-channel detection there. The data then is output, as we'll see in a bit, on the screen over here to give us elemental compositional information about the sample surface. The intriguing part of this technique is that only photoelectrons that are generated within a few nanometers of the surface of the material that we're looking at are actually collected and analyzed. So this makes this an extremely surface sensitive technique. It's one, therefore, that requires very high vacuums in order to maintain the cleanliness of the sample, but it also gives us elemental information and molecular information about the very regions of a sample that are important in both organic solar cells, organic light-emitting diodes, and organic field effect transistors. So once the sample is in the position in the center of the analytical chamber, having been transferred off of this sample rod, we'll do some additional adjustments here of both the z-axis and the x and y-axis to make sure that we're in the appropriate position to collect the maximum flux of X-ray or UV photons, and then to collect the maximum amount of emission in the electrostatic lens. There's also a possibility for us to rotate the sample on this axis so that we can do what's called angle-resolved photoelectron spectroscopy. If we rotate back at a certain angle, then we will accentuate the photo emission from the near surface region only, so we can really step up the sensitivity in terms of our ability to do surface analysis. These photoelectrons that are collected have kinetic energies that are directly related to the element from which they were ejected. All right? And the conservation of energy equation says that the kinetic energy of the ejected photoelectrons is related to the source energy, the excitation source, whether it be these X-rays here or UV photons, the binding energy of those photoelectrons, and then finally the work function of the spectrometer. So one of the key features of modern X-ray photoelectron spectrometers is that we use monochromatic X-ray sources as opposed to what we were using 20 or 25 years ago. This is the actual X-ray generation tube right here. We use a high energy beam of electrons to strike a target material. That the target material then gives off X-rays, in this case aluminum K alpha X-rays, which are brought up to this quartz crystal monochromator along here, and then finally brought to focus at the actual sample. The reason for the need for monochromatic X-rays is because it lowers the background that we have to contend with in the photoemission spectrum. It also increases the spectral resolution, which makes it possible for us to distinguish different molecular forms on the sample surface. It's quite critical. You give up a lot of signal intensity when you go through a monochromator, but we more than make up for that with the multi-channel detection on the back side of this system. Here's an example of a carbon 1s spectrum that was taken by this X-ray photoelectron spectrometer on a thin film of single-walled carbon nanotubes. And what we're looking at here is the counts, number of photoelectrons emitted as a function of their binding energy on this axis right here. What we see is in this carbon 1s region two very clearly defined peaks. This one corresponds to what we believe to be the carbon atoms in the core of the single-walled nanotube. These carbon atoms right here are at slightly higher binding energy. Those are covalently attached to oxygen or to chlorine as a result of the doping of these carbon nanotubes. And you can see that what we've had to do, because they're poorly resolved, is to deconvolve or spectrally fit the carbon 1s region here so that we can get a clear idea of what peaks they are. what their binding energies are, and then we'll match these against standard materials so that we have some idea of what the molecular composition is of this material. These are all photoelectrons that have been collected probably within the top 5 to 10 nanometers of this thin film surface. Okay, occasionally we want to characterize the interfaces between organic thin films and single crystal substrates. This part of the overall surface analysis system is devoted to what's called low energy electron diffraction, which is a technique that we use to first of all verify that we have a single crystal substrate, and then to probe the molecular architecture of an organic film that's been deposited over the top of that single crystal. So in the center of this chamber is a sample that's situated on this rod, which can be heated and cooled. This is situated at the focal point for an electron beam along this column right here to illuminate the surface, and the backscattered electrons, which again are very surface sensitive, will form a diffraction pattern that we'll go ahead and take a digital image of right here. So the process will involve creating the atomically clean surface. We can transfer it into this chamber for analysis to verify that it's atomically clean, bring it back over here to do the electron diffraction experiment. Then we can deposit an organic layer over the top of that, again in another part of the chamber, bring it back in here and re-verify that we have a very well-ordered organic film.
When we want to load a sample into the Kratos, we use this fast entry lock. So what this is a large evacuated cylinder that has a transfer arm in it. And we have a valve in between the regular chamber and this fast entry lock. So we can bring this back up to atmospheric pressure, load our sample, and quickly pump it down before transferring our sample into the chamber to do our analysis. So to load the sample, we put it on our little sample holder and put it onto the arm. Then we close the door and pump it back down.
The sample is mounted on a holder that has 2 grooves around its base. The manipulation tools have jaws that fit the holder. Using these tools, it is possible to transfer samples from section to section of the apparatus, even going around right-angled corners. The arm holding the sample and the analytical mount are controlled with wheels. During transfers, you have to manipulate both while watching through a viewport. The manipulator arm transfers the sample to the analysis chamber.